verification and acceptance, and then we'll round off with any questions and we'll send you a follow-up quiz. So we're going to start with a little bit of an introduction as to who we are at Intech. You can see here, Tim Combs is our president, and Bill, Luke, Jack, and Jim are all of our sales managers, with Bill focused on national sales. Luke Curley is responsible for sales in the upper Midwest. Jack Hauk is responsible for the Southeast region, and Jim Sorrell is our Hydroway sales manager. Sean Hibbets and myself are both the engineers here, and we have Josh, Chris, James, and Eddie handling our warehouse duties. Now a little bit about who we are. So these are our main product offerings, but not the only products that we offer, and you can visit our website to see a more inclusive list of everything that we provide here at Intech. So Chance and Atlas, that's our main product families under the Hubble group, with Chance being our helical anchor products and Atlas being our resistance pier products. MagnaCore is our non-domestic hollow bar micropile line, and Hydroway is our geosynthetic wrap strip drain product used in applications such as retaining walls or basement waterproofing, and even sometimes venting applications for venting methane gases. We also have Carbon Bond, which is our carbon fiber reinforcing product, sold in cloth strips with resin used in crack repair and reinforcing concrete applications. So shown here is the typical project lifecycle flowchart and how Intech adds value each step of the way. The first step of the project is consultant generating a recommendation, or basically a plan set. And during this step, we can provide education and resources to the consultant in order to ensure pile design is economical and feasible. We also offer design submittals during this step of the project. The next step of the project lifecycle is the owner engaging with the general contractor. And at this phase of the project lifecycle, we can provide education and resources to both the owner and the general contractor. We can assist the general contractor with finding a qualified pile installer through our vast network of installing partners. And the final step before project completion is the general contractor engaging a specialty contractor to perform the deep foundation work. So during this step, we can provide design submittals to submit to the owner and the engineer of record. And we have a network of engineers we work with to sign off on the submittals that we do in-house. And we can also offer construction phase assistance, like guiding a partner through their first time installing a particular pile type and performing on-site load tests. We stand by our partners and assist them, every step of the way through the project, whether that be, in situ conditions don't line up with our anticipated conditions, and we'll come up with a solution to ensure that project is a success. So we currently have offices located in both Caseyville and in St. Louis, with St. Louis being our main hub and Livonia, Michigan acting as our Detroit hub. We recently added an addition to our team, with Jack specifically focused in the Southeast region out of Atlanta, Georgia, focused on hollow bar and Hydroway sales. So this here is the area where we sell our Chance and Atlas products. It's mainly the upper Midwest and some of the Northeast regions. So for our MagnaCore products, we sell those nationwide. We're not limited to any particular region. However, we do most of our sales in the Midwest and Southeast. So our Hydroway distribution operates a little more globally. We have some partners that operate throughout Europe, and we're able to distribute that product anywhere. So we always like to open our presentations with a safety brief, because everyone has someone that cares about them and their safety. You can see the list here of potential people that care about you: your spouse, your family, your friends, your boss, and so on. And you have to understand that what you're doing, it doesn't just impact you; it impacts everyone around you. So if you think that someone would be worried about what you're doing in the field, you need to reevaluate that and come up with a way to do what you're doing safely. The goal is to go home every day, period. Not go home with an injury, go home safe to your families. Specific to load tests, uh, there are many safety concerns, when it comes to installing the pile and actually performing the load tests. Overhead equipment, you've got excavators, going around the job site, picking up load test beams, picking up load jacks. You have to be aware of your surroundings and, make sure you're not going to be in the way of an excavator rolling around. Don't stand behind excavators. Seems like common sense, but, just being aware goes a long way. Utilities, you have to call in your own utility locate. It's your responsibility to make sure that you don't encounter any utilities, and you can't rely on either an old utility locate or one that was performed by someone else. You need to follow all the OSHA and shoring requirements, eye and ear safety, safety glasses, earplugs, inhalation safety, especially when you're dealing with grout. If you're installing a micropile or a pull down pile, you're dealing with grout, you want to make sure you're wearing a mask if you're the one breaking the bags or near it. Pinching points and cuts, as always, when you're installing a helical pile or you're putting a load jack, on your test frame, there's a big pinch point there. So you need to make sure you're keeping your hands free of anything that can crush your fingers. High stress and torque releasing, when you're installing a helical pile, you can have upwards of 10,000 foot-pounds of torque acting on it, and you don't want to be there if that releases and staying right in front of it. So you also never want to stand in front of a loaded element during a load test. Just exercise caution. Also, you want to make sure that you're aware of your own body and make sure you're hydrated and that your muscles aren't fatigued to the point where you're going to drop something and cause a catastrophic event. So just make sure that what you're doing follows all your safety regulations and using common sense. So to start us off on our topic today, we're going to first start with talking about the purpose of a load test. So the main purpose is going to be to verify the pile performance. There's a few components to that with geotechnical capacity, structural capacity, and serviceability. So the geotechnical capacity refers to the soil's ability to handle the stress imposed by your deep foundation element. The structural capacity refers to the ultimate capacity based on a section of material properties of your pile. And the final performance criteria is going to be serviceability and deflection requirements. So there may be limits on the deflection at the service load level on your specific type of structure, whether that be because of the location you're at or, because of whatever type of structure you're building. You need to also make sure you're meeting the building code and project requirements, that you're meeting those serviceability requirements we just talked about. You need to justify that the loads and stresses are exceeding the code, and verifying your construction processes. So the load test step is going to be a chance for the owner and the engineer of record to understand how you're installing these elements, and they're going to be able to see in the field that, hey, we agree with how they're doing this, or maybe they might point out this step that they don't agree with how you're doing something. So it's a chance before the actual production piles begin to kind of catch any of those errors before it becomes a bigger issue. And even in certain circumstances, you may be able to value engineer a job based on the in situ conditions you found performing the load tests. There are several cases where, based on just engineering judgment and understanding of certain soil characteristics, you can estimate a shorter pile and then prove that out, with your load tests. So now we're going to talk about the ASTM and who exactly they are and how they play a role in load testing. The ASTM is the American Society for Testing and Materials, and they're an international standards organization that develops and publishes voluntary consensus standards for a wide variety and range of materials, products, systems, and services. And they operate over 12,000 standards globally. So the ASTM is typically the standard that we see and use in regards to deep foundation load testing. However, this may be subject to state or local municipality specific standards. Some municipalities have their own rules that are more or less strict than the ASTM, and it's important to understand this before you're doing your test to make sure you don't have to repeat the load test if you didn't follow those local standards or you didn't follow the ASTM standard. So these are the three most important ASTM documents as they pertain to load testing of deep foundation elements. So ASTM D1143 goes over compression load tests. ASTM D3689 goes over tension load tests. And ASTM D3966 goes over lateral load tests. So in each of these documents, there's a lot of critical information in there as they pertain to load testing. They each go over the test foundation preparation, the apparatus for applying and measuring the loads, and the apparatus for measuring the movement of those, the procedures for performing the load test, recording the test readings, any safety requirements, and their guidelines for what the report should look like. And all this is important because the ASTM is going to be the general governing guidelines that inspector is going to be looking for, while he's on site. So the engineer of record, the inspector, the owner, they're likely going to be referring back to these ASTM documents, and how you're following them when you're performing your load test. So now we're going to go over some of the test types and setups. It's important to note that the topics I'm going to discuss here are not specific to any type of pile, and they can be generally applied to almost any deep foundation element. In general, the testing process for a helical versus the micropile is going to be essentially the same. So shown here in this image is a compression load test and all of its components. First, you can see that this main beam right here in the middle is the load test beam. The spreader beams are off to the sides here. Then your 4 reaction anchors. Then your reference frame for measuring the loads. Your hydraulic jack. Your actual test pile sitting underneath that hydraulic jack. Your dial gauges to measure the movement. And the cribbing materials that your load test beam is setting on. And as you can see here, when the jack loads up the test beam, it's going to be pushing up on that test beam, which is then going to push up on the spreader beams. And as the spreader beams are being pushed up, the reaction anchors are then going to be loaded up in tension. So it's important to note that we have shown 4 reaction anchors in this load test setup here, but you can have 2 reactions or even up to 8 reactions as necessary. You need to understand how these loads will be imposing on your reaction anchors to come up with a design for your specific load test that's going to provide sufficient reaction strength. So going over, how to actually set up a compression load test, your first step is going to be installing your test pile and installing your 4 reaction anchors. So I'm showing here in the bottom plan view that you need to have a clear distance from your reaction anchor to your test pile of 5 times the max pile diameter, or an 8-foot minimum. And although there's an 8-foot minimum required, most inspectors and owners are understanding of the specific ways that different pile types stress the soil. Like micropiles are friction-based, and they don't really develop much of a stress bulb that interacts with other piles. So you can, reduce that clear distance for micropiles, as well as helicals typically don't have a stress bulb that extends past 5 times the pile diameter, which is the minimum that they're calling out there. So a lot of times, that 8-foot minimum can be overlooked basically for your specific pile type. So after you've got your elements installed, you're going to place your cribbing materials and your hydraulic jack. And you want to ensure that your jack's at an appropriate height compared to the cribbing materials. So when you place your load beam, you're not maxing out the stroke length of your jack. Once you've got your jack in place, you then put your load beam on top of your cribbing materials, and you want to have it centered over the jack on your test pile. Once you've got that step completed, you're going to place your spreader beams on top of the load test beam, and then place the threaded bar through the spreader beams and screw them into the reaction anchors. After that step, you're going to lock off your reaction anchors with plates and nuts, and then load your jack to the alignment load, which is typically anywhere from 5 to 10% of the design load, and check that all your beams are level. If they're not level, you need to adjust the top nuts on top of the spreader beams here until you get everything level at the alignment load, and then unload. So once you've got everything level and set up, your next step is going to be to set up an independent reference frame. And this reference frame, according to the ASTM, should be adequately stiff in order to minimize vibrations that may give, bad readings on your dial gauges. And once you've got your reference frame in place, you can then place your dial gauges at opposite corners of your plate. So as you can see here, they're on opposite sides of the jack and the plate, and here as well. So they end up on complete opposite corners of the plate. So the ASTM outlines 7 different procedures for compression load testing, and we're going to go over each one of these. So firstly, procedure A, the quick test. This is the only test out of all the procedures that is not listed as optional. So procedures B through, I think it's G, they're all going to be optional load tests that aren't going to be required unless the engineer record says you need to perform procedure D from the ASTM. So you're going to first, for the quick test, apply the test load in increments of 5% of the anticipated failure load, and then you're going to add each load increment in a continuous fashion after recording the movements from the previous load increment. During each load interval, you're going to hold that load constant for no less than 4 minutes, and then remove the load when you're completed in 5 to 10 equal decrements, keeping the load constant for the same 4-minute time interval. When you reach the maximum load, which is going to be 200% of the design load, you need to use a longer time interval, usually 10 minutes, to assess the creep behavior of the pile. So as you can see here, the ASTM recommends a 5% load increment. However, most engineers and owners will accept or dictate that you use a larger load increment of 10 to 20%. The additional data that you're going to get from having a load step every 5% is not going to be as critical as having the final data on residual movement. And for this reason, larger load increments are often used because it saves a lot of time in the field. So procedure B, again, all these after the quick test are all optional. Procedure B is a little bit different. You're going to apply the load in increments of 25% of the design load and maintain each load increment until the rate of axial movement does not exceed 0.01 inches per hour. And after applying the maximum load and reaching an overall test duration of at least 12 hours, you're going to then begin unloading whenever the axial movement does not exceed the same 0.01 inches per hour or a max of 24 hours. And then after that point, you're going to unload in equal decrements of 25% of the design load with 1 hour between each decrement. So you can already kind of understand why procedure A, the quick test, is the go-to test that you see, because the other tests, can take up to 24 hours versus a quick test you can have set up and completed in a matter of, 4 to 8. So procedure C, loading in excess of a maintained test. So first, before you begin procedure C, you need to complete procedure B, the one before this. And after the loads from procedure B have been applied and removed, you need to reload the pile in increments of 50% of the design load, allowing 20 minutes between each load increment, and then apply the load in increments of 10% until reaching a maximum load which will be specified beforehand or failure. And if failure occurs, continue jacking the pile until settlement equals 15% of your pile diameter and hold the maximum load for 2 hours. Decrement the load in 4 equal decrements, allowing 20 minutes between each one. Procedure D is the constant time interval load test. So once again, you're going to follow the same procedures of procedure B, but instead of looking for a rate of settlement, you're going to use a 20% design load increment and a 1 hour hold for each load increment. Once you've reached your maximum load, you'll follow the same criteria from procedure B and then deload in 25% decrements, allowing 1 hour between each one. So procedure E is the constant rate of penetration test. In this procedure, you're going to vary the applied load as necessary to maintain a pile penetration rate of 0.01 to 0.05 inches per minute for cohesive soils and 0.03 to 0.1 inches per minute for granular soils. Hold the maximum load, which again should be specified beforehand. That's usually 200% of the design load, until you've reached a penetration of at least 15% of the average pile diameter, or until penetration stops. Once you've completed this, gradually release your final load to protect your load measuring systems. Procedure F, the constant movement increment test. During this test, you're going to apply the test load in increments required to produce pile movement equal to approximately 1% of the pile diameter. So vary the applied load as necessary to maintain each movement increment, and do not apply additional load until the rate of load variation to hold that movement increment is less than 1% of the total applied load per hour. Continue loading until the pile movement equals 15% of the pile diameter. Then you're going to remove your final load in 4 equal decrements. And do not remove additional decrements until the rate of pile rebound is less than 0.3% of the pile diameter. So procedure G, cyclic load test. Along with the quick test A, I would say this one is the second most common procedure that you're going to see. So during this test, you're going to use the same procedure from procedure B, the maintain test, using hold times instead of looking for a penetration rate. So after the application of the load increments at 50%, 100%, and 150% of the design load, you're going to remove those load increments equal to the loading increments that so you're going to have decrements decreasing load equal to the increments that you increase the load, allowing 20 minutes between each one. And after removing each maximum load level, you're going to reapply the load preceding that and 50% increments, allowing 20 minutes between each one. And after you've reached your max test load, hold and remove that test load in accordance with procedure B. So shown here is an image of a tension load test, and kind of going over the components of this. It's pretty similar to the compression load test with a few different caveats. So we have the main load beam right there in the center here. Then the cribbing materials off to the side. We have the hydraulic jack placed on top of the beam for tension load tests. We have the actual test pile itself, and the hydraulic ram and pump are out of frame here. And this tripod with the 2x4s is going to be your reference frame. So tension load tests are the preferred approach for most contractors, because you can see as the load jack pushes up on the plate here, it's going to be pushing down on your beam, which is going to push down on your cribbing material. And this greatly simplifies the setup of your load test, because as long as you don't have extremely soft soils underneath your cribbing, there's no need to place any tension, or there's no need to place any reaction anchors, unless, like I said, that there's really soft soil there, and in which case you may have to place a compressive reaction anchor underneath the ends. So like I said, tension load tests, they're a lot simpler, because all you need to do for the first step here is install your test pile, and there's no reaction anchors to deal with. So the second step for a tension load test is going to be placing your cribbing materials, and then placing your load beam on top of those materials. After you've got that in place, you're going to place your jack on top of your load beam and lock it off with a plate and nut after you've got your threaded bar going through the test beam and the load jack. Then at that point, you're going to set up your independent reference frame. Shown in that image, we had a couple tripods and some 2x4s, and you're going to place your dial gauges on opposite corners of the plate, kind of in a similar fashion to a compression test. So tension load tests have kind of a similar list of procedures. I think we're missing one procedure that they don't do for the tension load tests. But all the tension load test procedures, they basically mirror that of the similarly titled compression load test procedures. So I'm not going to go into detail about all these procedures, because we just kind of walked through each one of them. So shown in this image is a lateral load test setup. It's important to note that the lateral load test can be performed in a variety of ways. How I have it shown here is the reaction anchor is basically placed in a reaction frame specifically designed for tension load testing. But these elements can also be cast in concrete. The important thing is just to ensure that your reaction elements right here are going to actually be able to hold that lateral load. So the threaded bar is going to be going through your reaction frame and your test pile, and you're going to be loading it up with the reaction or with the load jack right here, pushing off on a plate and pulling this test pile. An important note is you can also place the jack on the other side of the reaction frame and push the load pile instead of pulling it. So setting up a lateral load test, out of the compression and tension tests, the lateral load test is going to be the most difficult to set up. And for that reason, we don't often see lateral load tests, as a requirement on a project. Typically, we can analyze lateral loads with software in advance and have that approved in the submittal process. And that typically covers, any lateral load, but you may be required to perform a lateral load test at some point. So the first step is going to be installing your test pile and your lateral load test bracket, and then installing your reaction anchors. So once you've got your reaction anchors in place, you can either A, cast them in concrete, or B, like we've shown here, place your reaction frame on top of them and thread bars through it and lock everything off with plates and nuts. After you've got the reaction frame set up, you can then place a threaded bar through your reaction frame and through your lateral load test bracket and lock everything off with plates and nuts. And as shown here, I talked about it briefly earlier, but you can see a little bit better in this image how whenever you load this jack, you're going to be pushing this plate and ultimately pulling this pile to the right. But if you set it on the other side, you're going to be pushing it instead of pulling it. So you're going to be pushing it to the left instead of pulling it to the right. The same with the compression and tension load test. You need to set up an independent reference frame with dial gauges to measure the movement. So here's a list of all the procedures that the ASTM outlines for lateral load tests. They're a little bit different than the compression and tension load tests. So procedure A, standard loading. Unless failure occurs first, you're going to apply and remove the total test load equal to 200% of the proposed lateral design load as follows in this schedule here. So it's basically 25% increments with varying hold times. So procedure B, excess loading. So after you've applied and removed the standard load test from procedure A, apply and remove the loads as followed. So you're going to ultimately go up to 250% of the design load for an excess loading procedure. You're going to hold that for 15 minutes. Procedure C, cyclic loading. Now this is going to be actually pretty similar to the compression and tension load test cyclic loading. You're going to apply and remove the loads as follows in this schedule off to the right here. So procedure D, surge loading. Surge loading involves the application of any specified number of loading cycles at any specified load level. So apply and remove the load levels at a uniform rate as shown off to the right in the schedule. Reverse loading. So this comes into play when I was talking about pulling versus pushing on the lateral load test element. So reverse loading involves the application of a lateral load test in either the push or pull mode. Test the pile first in one direction and then test it in the opposite direction. And it's going to be specified which loading schedule you're going to need to use beforehand. Reciprocal loading, it's a little bit trickier than the reverse loading because at each specified load level, you need to then load in the opposite direction after you've loaded your first load step to the right. You need to then do your first load step to the left. Hold each peak and zero load until the deflection readings can be taken. So to specified lateral movement, procedure G, you're going to apply the lateral load test in accordance with the previous procedures until the gross lateral movement of the test pile is as specified. And then you're going to remove the total load and 4 equal decrements, allowing 10 minutes between each one. So procedure H, the final procedure for lateral load testing, is the most involved out of all the procedures because, and probably tell you the most about the pile in reality. Because during this test, you're going to apply a specified axial load before applying your lateral loads. So you'll be able to understand how that pile is going to behave a little bit better than just applying the lateral load by itself. And it'll be specified, which procedure for your loading schedule you need to use beforehand. So now we're going to talk about pre-production load tests. So pre-production tests should be performed to verify the suitability and ultimate capacity of a proposed pile. These should be performed prior to the installation of the production elements and can be used as a tool to value engineer based on in situ conditions. Production anchors must be identical in terms of design and construction methods. So the owner, the engineer of record, and inspector, they're all going to be watching how this pile is installed, and it's going to be your responsibility to ensure that your actual production elements, mimic those construction methods basically to a T to ensure that the actual production piles are going to have the same type of performance that your test pile did. So an actual production load test or proof test is a test performed on an actual production element. And if these proof and production load tests are required, it's going to be predetermined by the engineer of record and the owner. It's not going to be up to you. So typically we'll see that they'll call out maybe 5 to 10% of the production elements must be tested. And unlike the pre-production tests, it's not advised to test these all the way to 2 times the design load factor of safety, because you wouldn't want to damage the actual production pile. So tieback load tests, you have a few different criteria for these. You've got a performance test, which is the number of production elements will be determined by the engineer of record and the owner beforehand, and it's a test to 1.25 times the design load and of an actual production element. Then you have a proof test, and the engineer of record once again may require that some or all elements that aren't performance tested be proof tested. And this is used as a less involved check of anchor performance, and unless you have undesirable results, you can move on. But if you do have undesirable results, they may call out that you need to perform an actual more detailed performance test on the adjacent elements. And in certain circumstances, you may be required to do extended creep tests. So if you have a site with soils that have high strain characteristics, they may want to understand how that load's going to act on those tiebacks over time. So I'm going to touch a little bit on beam design and selection. Beams are designed based on the applied moment, based on the ultimate load. And then you're going to take the required section modulus out of the steel manual to sustain that moment. And our beams are typically designed as either 2 W beams or 2 channel beams. And that's essentially so that you've created a void in the middle in which you can, slip your element through. In certain circumstances, you can do just one larger W section that doesn't have any hole, but you're going to be limited in what you can do with that beam long term if you don't have the accessibility to, stick threaded bar through the actual beam itself. Like I mentioned on the last slide, once you've got your section modulus, your required section modulus, you're going to look in the AISC steel manual to select an appropriate beam that can handle that desired moment. And the required section modulus will be cut in half when you're designing a load beam that has 2 identical sections of beam. So from here, it's not the whole story for designing the beam. You would then need to design the plates like shown here that connect your 2 beams together, as well as bearing stiffeners, right here and where the spreader beams are. And I'm not going to get in the engineering weeds of designing those stiffeners just for the sake of time, but this is in a nutshell how you need to design your load test beams. So now we're going to go over the data collection side of things during a load test. So the most important thing when performing a load test is to make sure your jack calibration is up to date. You may be asked to furnish this calibration report for your jack as part of your load test report or before you do your load tests. The most important information you're going to find on this calibration report is down to the right here. It's how your pressure relates to a load for the specific load jack. So with the information you have in the jack calibration report, you can generally create a linear equation to represent the load as a function of the pressure gauge reading. And with this information, you can fill out a load test sheet with all the predetermined pressure increments necessary to complete your load test. And by understanding this in advance, you can properly set up your load test sheet so that you can avoid any confusion in the field when you're actually performing the test. So you need to select a jack that's going to work for your specific application. You need to first make sure that you're in the middle 60% of your jack's capacity. So like shown here, these 20% off to the left may not be the most accurate readings, and the 20% off to the right at the max jack's capacity, it may be harmful to the jack to run it that high. So you want to make sure you're in the middle 60% of your jack's capacity. And you also need to make sure you are picking the right type of jack. So as you can see in the images here, this one is a hollow ram jack, and this is a solid ram jack. And you need to make sure that your hole size is going to be adequate for your pile type, and you need to make sure that your stroke length is going to be adequate for your load test as well. And like I just talked about, you also need to make sure you're within that usable load range. So hydraulic pumps, you should have a pressure gauge attached directly at the outlet of the pump here, and then redundant pressure gauges. Sometimes you want to put two pressure gauges in line in case one of the pressure gauges is failed or inaccurate. You can pinpoint out that during the load testing. It's not a requirement to have two pressure gauges, but if you have two, you might as well use them. So it's important to exercise judgment in the field when trying to maintain a consistent load. A rule of thumb, when the pressure is dropped by maybe 50 to 100 psi, you should then bump the hydraulic pump to maintain your target pressure. It's not going to be possible to maintain an exact pressure, precisely. So if your target is 600 psi, it's going to fluctuate. But the goal here is to make sure that you're, on target as possible. Now this may seem like a little bit of a rudimentary step, but understanding how to properly read the dial gauge is a critical step for an accurate load test. If you don't have accurate dial gauge readings, well, your load test isn't going to be accurate. So the small dial gauge in the center of the face here is showing the macro movements, which is like tenths of an inch. So shown on this specific gauge, the dial gauge is reading 7/10 of an inch or 0.7 inches. And the large dial, around the outside is going to be reading your micro movements, which are thousandths of an inch. So in this case, we have 97 thousandths of an inch or 0.097 inches. And you're basically going to add those two readings together to come up with a total dial gauge reading of 0.797 inches. So as discussed earlier, proper dial gauge placement should be on the two opposite corners of your bearing plate. And this is done so that if you have any differential movement across your plate, let's say one side's reading 0.8 and the other's reading 0.85, you can use the average of that to have a better understanding of your actual pile deflection. So this is an example load test sheet, which is basically what you're going to be bringing out in the field beforehand. And your load increments and procedure that you're going to be following should be determined by the engineer of record or the owner before you perform your load tests. At this stage, when you've got your procedure and load increments, you're going to want to fill out all your pressure targets, so you're not trying to do this on the fly in the field. You can have up to 4 dial gauges, but like we talked about in the previous slides, only 2 are required. The more you have, the more accurate your data is going to be, but 2 on the opposite corners of the plate should be sufficient. You also need to make sure you have an area for notes at the bottom of your load test sheet. for any special, cases that arise during your load tests. Let's say you notice the reaction anchors pulling out a little bit. That might be something you'd want to put in the notes here, or just anything that could affect your load tests. You want to make sure you've got a record of that. So we have a job box that basically includes all the equipment you'd need to perform a load test. We have several different types of load jacks as well as load beams themselves. And when we run out this equipment, everything is up to date on the calibration data, and we can assist you in setting up your load test sheet to set you up for a successful load test. So now we're going to go over the interpretation and acceptance criteria for load tests. There's many criteria for determining the acceptance of a pile load test. So for instance, the FHWA, the IBC, and state and local codes, or the engineer could come up, the engineer record could come up with his own acceptance criteria based on serviceability, of that specific location. It's not going to be up to you to determine which criteria you're going to be using. This should be outlined to you by the engineer of record or the owner beforehand, just so everybody's clear, before you begin your test as what your target is. And at the end of the load test, capacity is going to be reviewed basically at an ultimate resistance limit and a serviceability limit. So the ultimate resistance typically consists of two elements. You've got your geotechnical capacity and your structural capacity. I touched a little bit on that earlier, but I'll talk about it again. So the geotechnical capacity is going to be your soil's ability to handle the load, and the structural capacity is the actual steel and or grout ability to handle that load. And the serviceability limit deals with the deflection of a pile at that service load level. It also deals sometimes with differential settlement in a structure. So this should all be outlined what these limits are going to be before you begin your load test. So the specific criteria for both capacity and serviceability, as I just talked about, it's not going to be up to you. It should be clear from the engineer of record or the owner beforehand. If it's not, you need to contact them to make sure everybody's on the same page. Understanding the specific load test acceptance criteria before you're performing the load test is going to ensure that you're not in a situation where you perform an incorrect test procedure, or you're shooting for a certain pile deflection, and it's just not going to set you up for success if you don't have a good understanding of what the goals are. And at the end of a load test, there's going to be essentially two things that can happen. You can pass or you can fail. And if a load test passes, the next step is generally going to be to install your production elements. If your load test fails, the next step is going to be up to the engineer of record. You may have to install, an entire new load test element and reaction anchors. You may be able to get away with just installing, if you've got a helical, they may say to spin it deeper. But it's going to be up to the EOR. He may also, allow a reduced factor of safety on the ultimate load. So if the pile performed to 180% of its expected capacity, he may take that 1.8 factor of safety instead of a target of 2. So it's going to be up to the engineer record what the next step is going to be. So this figure to the left displays an incremental load test. And as you can see here, there's only going to be one measurement of residual movement at the very end of applying the final load. Versus the figure to the right, this is the cyclic load test, which again, I said is the most common, apart from a standard quick test. And this offers residual movements for basically, several load steps throughout the entire load range. And this could be useful for, specific serviceability requirements at the service load level, and understanding residual movement at each one of these steps, along the entire load test. So this figure is a graph of a tension load test on a helical pile. And the blue line is the measured strain on the plate in the field. And the green line is the ultimate capacity based on an IBC code for helical piles. So this green line for the ultimate capacity is specific only to helicals, and there's going to be basically a different standard, depending on what what local code you're using, whether it be the IBC, state codes. There may be a different type of ultimate capacity requirements also based on your pile type. So the red line at the bottom here is the elastic tension in the bar, which is PL over AE. And then the ultimate capacity in the IBC here is that elastic tension plus 10% of the average pile diameter. And for any given measured strain, you can calculate the actual strain by subtracting out the elastic strain of the bar. So residual movement after the load test is completed is going to be likely the most important reading, as well as the service load movement to that engineer of record and the owner to determining whether or not that test was a pass or a fail. So a more detailed view of that cyclic load test. This is the total residual movement over the whole test, and each one of these steps here is residual movements at different load levels. With one time the design load being a critical one, as that's usually what is going to be your service load level. So this residual movement right here is going to be a really important reading, and this total residual movement is another really important reading.